Hello, everyone. Welcome to another section on data structures and algorithms. This lecture will be on self-balancing trees. At the completion of this lecture, we expect you should be able to explain the impact that balance has on the efficiency of a binary search tree. Also expect you should be able to explain how balancing factors are used to indicate when a tree is unbalanced. In addition, we think you should be able to explain how rotations can be used to keep a binary search tree balanced. And lastly, you should also be able to describe, create, and maintain an AVL tree. Before we go further to discuss other things in this lecture, let's have a look at the complexity of a binary search tree. Assuming we want to perform operations such as searching, insertion, and deletion on a binary search tree, the ideal case scenario is when the complexity is of the order of log n, or sorry, log n, yes. But the worst case scenario is when the complexity is of the order of n. So in the case of being on the order of n, in that case, we need to iterate through all the nodes within the tree before we get the value that we are searching for. So now let's see how we can build a binary search tree. Considering the condition or the rules for building a binary search tree, we can simply generate different structures if we are given a binary search tree that has 3 nodes. Likewise, similarly anyway, you can also generate different structures for a node with for a tree with 4 nodes, and that also for a tree with 5 nodes. So let's have a look at this. Now we want to generate build a binary tree for a tree with 3 nodes, A, B, C. So we can build the binary tree to look like this. It can also look this way, can be like this, and this, and that. So for a binary search tree with 3 nodes, we can generate 5 possibilities of trees. And if you look at these possibilities of trees, you realize that all of them, they have different structures and different looks. So, and again, the structures determine the height of each of these trees. For instance, this tree has a height of 3, which is 1 level, another level, and another level, which is 3. But this tree, for instance, has a height of 2, which is level 1 and level 2. So that implies that the height of that tree might determine the complexity. So despite the number of nodes, the number of nodes might not be the factor that will determine the complexity, but the height might be the factor that will determine the complexity. And that also explains that the structure or how the tree looks or arranged will contribute to the complexity of the tree. So for a binary search tree with 4 nodes, we can also generate different structures. So in this case, we have about 14 possibilities. And similarly to what we did in the other one, the complexity on this in terms of the height is 4, but the complexity on this one in terms of the height is 3. So you see the difference. And also reminds us that the structure or how they are being structured will contribute to the complexity of the system or of the binary search tree. So these are some of the problems with the binary search tree. And if you perform this, if you follow the pattern we used to generate the trees in the previous two slides, you can also generate that for the 5 nodes. So yes, here we are trying to say that the shape of that tree goes a lot to tell about the complexity of that tree that you are generating. So what do? We need to find a way to reduce the height of that tree. And one way to do that is by using the self-balancing binary search tree. So yes, the self-balancing binary search tree is one that automatically keeps its height as small as possible at all time. And it goes about keeping its height as small as possible by performing what is termed rotation. So rotation is being performed on that tree to reduce the height. Rotation can change, we change the structure of the tree without changing the order of the elements. So yes, you can change the structure like we saw in the previous slides that we can generate different structures. So we can change the structure, but it cannot change the element or the order of the element. I'll tell you more about the order of the element in subsequent slides. So another major approaches to other major approaches to perform this operation are the AVL using the AVL tree or using the red black trees. But in this case, we're only going to focus on the AVL trees. So let's now look at the tree rotation. So a tree rotation is used to change the structure of the binary search tree without changing the order of the elements. This is exactly what we said in the previous slide. Now let's explain what we mean by changing the structure without changing the order of the elements. So if we perform a tree rotation on this, what we're going to have is this tree. And now you see that the height has been reduced from 4 to 3. So it has changed the structure, first of all, but did it change the order of the arrangement of the elements? No, it did not. It did not because 2 is still, let me start from 3. 3 is still at the right side of 2, and 2 is still at the left side of 5. Let me leave 6 for now. Then 8 is still at the right, 9 is still at the right side of, I have to go through it again. 3 is still at the right side of 2, and 2 is still at the left side of 5. And 9 is still at the right side of 8, and 5 is still being attached to 8 at this point. So now what we are now facing is this one, which is 6. 6 is at the right side of 5. So if you come to 5, this is the right side of 5, and this is where 6 is located. So in this case, we have changed the structure, but we have not changed the order of the arrangement of the elements. So with this, we can use these algorithms here to achieve these changes. And the algorithms will be explained later. The only thing I want you to identify from this algorithm is that this is called the root node. Now let's move to the next slide. So for this activity, we have to rotate this tree to make it balance, or to rotate this tree anyway. So how do we perform the rotation? We have to look at the root nodes. This is the root node. So when we finish the rotation, because our point or the reason why we want to perform the rotation is to reduce the height. So this is 1, 2, 3, these 3 levels. So the height here is going to be 3. So we want to reduce the height. So now we have to identify the root node and identify another node that we call temp. So when we have done that, we can move the temporal node to replace the root node. And we take the root node to the right. So then at end, we're going to have a structure that looks like this, finally. I'll tell you another way, a simple way to achieve this. Another simple way to achieve this is we can put something that looks like a nail somewhere here and assume that we have a rope to pull this down. So if we pull this 4 down, the 4 is going to be here, finally. The 3 is going to move to this place, and the 2 is going to move to this place. So you have this structure which represent this after your rotation. So now I have to erase these things. We'll see more examples anyway. Yeah. Now we want to perform another operation on this one, rotation operation on this particular one. On this one, we also have to identify the node, the root node, and we have to identify the temporal node. So if we identify the root node is this one, 3, and the temporal node is this one, which is 6. So what are we going to do? If we use the same pattern from what I explained earlier, you still achieve this process. However, we can do this by, first of all, looking at the temporal node. And that temporal node is going to replace the root node. So if it's going to replace the root node, that tells us that 6 is going to be at the top. And for 6 to be at the top without changing the arrangement for 9 and 7, then we can break it to look like this, 6, 9, 7. So what we are left of right now is let me pick this. If we break out this, we have this. Because we want 6 to replace the root node, which is 3. And what we are left with is 2, 3, and 5. So if we have 2, 3 here, and we have 2 here, then 5 is somewhere not attached to anything. So now let's start with this, because this is now the root node. If this is the root node, then the next step we're going to take is that we're going to connect this to go with this one. Okay, so 6 is our root node. Then we have linked 6 because the 3 and 2 are the left side of 6 to this point. And what is left is 5. The first question we're going to ask ourselves is, what is the position of 5? From this place, the position of 5 is that 5 is on the left side of 6. So 5 is not going to come anywhere here. So it's going to come on the left side. And when you move to the left side, the first element you're going to meet is 3. So what are you going to do? Looking at 3 and 5, we realize that 5 is greater than 3, so it's going to take this position. This is the final structure we're going to have. So if we look at the final structure, we have something that looks like this, which is similar to what we had earlier. That is 6, 9, 7, 3, 2, 5. So this is how you can achieve the rotation. So in the subsequent slide, you also see more examples and more approaches to achieve this kind of rotation. And this algorithm explains the process that we have taken, as finding the temporal file and replacing it with the root node and moving the root node either left or right, depending on the structure. So we're going to explain when you need to move it to the left and when you need to move it to the right later. So now we'll be moving to the AVL trees. So the AVL trees is a kind of a binary search tree, but it has some conditions attached to it. The first is that the height of the left subtree, let me put it this way, the difference between the height of the left subtree to the height of the left subtree to that of the right subtree must not exceed 1. So what do we mean? What we mean is that if you have a node here, you have anything at the left is the left subtree, and anything at the right is the right subtree. So the difference between the left and the right must not exceed 1. And that makes that tree an AVL tree. So let's determine if these trees are AVL trees. So first I'll pick my pen here. This is to the left we have 0, to the right we have 0. So it's 0 minus 0, which is 0. 0 minus 0, which is 0. So the difference is not more than 1. So this is an AVL tree. Then you come to this place, we have 1 at the left minus 2 at the right. So we're going to have minus 1. So in terms of difference, this is not more than 1. More than 1 in terms of difference, not in terms of value. So if we do the same thing here, we have 3 nodes at the left and 2 nodes at the right. So 3 minus 2 is 1. So all these trees are AVL trees because the difference of the subnode to that of the right uh, sub subtrees, pardon, is not more than 1. So let's have a look at the next slide. So the next slide has 4 trees that we want to find if they are AVL trees. I'll leave you with this one to solve. If you follow the same pattern, you will determine if any of these are AVL trees. Okay, so on the AVL tree principles, there is a term that is referred to as balance factor. And that balance factor is for each of the nodes within that AVL tree. So the balance factor is referring to the difference from the child to at the left and the height, sorry, let me put it this way. The difference between the left subroot, the height of the left subroot to the height of the right subroot. So, and for any node to be balanced, that the difference between the left and the right subtrees must not be more than must be either +1, 0, or -0. So in a case where that node has a balance factor of +1 or -2, that node is considered unbalanced and it needs to be rebalanced. With examples, you can understand better what we are explaining here. So let's have this as an example. So we start with this one, the leaf node. How do you determine the balance factor? The balance factor is check if there's any node at the left, subtract it with the number of nodes at the right. So here we have 0, 0, which is equal to 0. Then you come to this place. There is one node at the left, but there is no node at the right. So that is 1 minus 0. That is why we have +1. So if we consider this one, we have that at the left there is one node, but at the right there are two nodes or subtrees. So it's going to be 1 minus 2. And 1 minus 2 is going to give us -1. And this one is 0 because of the same thing that happened to this one. So this is how you can find out the balance factor for each of these nodes. Now, we can add a node to this to make it unbalanced. So you can add any node. If you add a node, for instance, to this place, then the node will become unbalanced because this node will become unbalanced because let's have a look. To add a node somewhere here, you can try that anyway. This node becomes 0. This node becomes this minus this becomes 1 anyway, minus 0, which is 1. Okay. Then in this case, you have at this point, you have 1, 2 minus 0, which is going to be 2. So it's going to be plus 2 at this level. So this node now is unbalanced. And if you continue with the operation, you can have multiple nodes that are unbalanced. And what we need to do, because we need to rebalance them. So let's move further with other examples. So this is another node that we want to find out the balancing factor, the balance factors for, for the nodes. So if we take the same process at this point, there is no sub 3 at the left, and there's no sub 3 at the right. So the balance factor will be 0. For this as well, it is going to be 0 because of the same reason here. This is going to be 0, this is going to be 0, and this is going to be 0. But you can put it this way that for all leaf nodes, the balance factor is always 0. Then for this one, it is 0 because we have only one node or one subroot at the left, and we have another one subroot at the right. So if we subtract it, we're going to have 0. This is applicable to this. And if we project it to this place, we're going to have 2 minus 2, which is 0. So for this one, we're going to have 3 minus 2, which is plus 1. So this is how we can get the balance factor for each of these nodes. So the question is, where can you insert a node that will make this remain an AVL tree? You can insert a node somewhere. I'll give you a clue. You can look around at somewhere here, then see if you can insert a node somewhere to make it an AVL tree. And I will ask you to try and insert a node, another node to make it unbalanced, or to make any of these nodes unbalanced. Now, let's now have a look at creating an AVL tree. We are creating an AVL tree by adding a node to the root node, or to the subroot, or to the leaf node. So now it's similar to the pattern we use when we want to create a binary search tree. So in this case, we see how we can insert data into the AVL tree. So we also make sure that we maintain the principle by ensuring that the AVL tree is balanced. Now, in a case where the balance factor for any node changed to +2 or -2, that node is now is not balanced. So, and we need to perform operation to make it balanced. So the kind of operation we perform to make it balanced is this rotation operation. And the rotation operation takes place at the unbalanced node. And the next place where it can take place is at the child of that unbalanced node, or at the grandchild node of that unbalanced node. With examples, we can understand better anyway. But the point you have to pick at this place is that first, that for any node to be unbalanced, the balance factor will be either +2 or -2. And we use rotation to make that node balance. Depending on the kind of unbalanced node that we have, That will determine the kind of rotation that we're going to perform. So in AVL tree, we have 4 distinct rotations that we can perform, but those rotations can be grouped into 2, called the single rotations and the double rotations. So on the single rotations, the rotation could be by left-to-left rotation or right-right rotation. So that is like it is done only on one side. But for the double rotation, the rotation is either left-right rotation or right-left rotation, which means you perform the rotation at the left, either at the left first, then the right follow, or at the right first, then the left follows. So yeah, and the rotation takes place at for any node with the balancing factor of plus or minus 2. Now let's pick the single rotations. So for the single rotation, we want to explain further. We want to say that the unbalanced for the unbalanced node and the unbalanced node and the left subtree of the unbalanced node are both left heavy. So that is saying that for this LL rotation, what caused it to become unbalanced is that the unbalanced node itself and the left subtree. So because we added a node at the left, that makes it unbalanced. So then further we can explain by saying that the balance here should be said balance factor, not just the balance. The balance factor of the unbalanced node is +2 for LL rotation. And the balance factor of the left child of that unbalanced node is +1. And how we can rebalance them is by performing a single rotation towards to the right around the unbalanced node, which is referring to the one that has +2 value. So this is an example of a, a tree that we want to perform a rotation to make it balance. So first of all, we have to find out if this is left-left rotation. It is left-left rotation because we added another node at the left of the root node. And because of this node that we added, it's because of this node that we added that the value of the balance factor of 8 becomes +2. So what do we need to do to make it balance? We need to perform a rotation. And that rotation is going to be a rotation of which is a question for you to answer. So let's continue. I know you are cracking on it, but let's continue then. So we perform the rotation by going, rotating to the right. And if we rotate to the right, we're going to have this structure. So the height of this structure has reduced to 3. And you can use this algorithm to achieve this by, first of all, finding a temporal phi, which is 5, a temporal node, pardon, which is 5, and 5 replacing the position of the root node. When we do that and take this one to the right, because we are rotating to the right, then we're going to have this. Also, I want to remind you again that if you look at this node, you realize that something like this happened, like a nail was fixed here and a rope was fixed this place to pull this down. So when you pull it down, this goes up to this location and this remains. That's why you have 5, 2, and 3. That this has already gone down. And if it is going down, if this is a nail, then this is going to be under 5. And you have 8, 9. What you have left is 6. How do you fix 6? You fix 6 by considering this node, knowing fully well that 6 is at the right hand side of 5. So 6 must also remain at the right hand side of 5. So you have to look at this place. Where can you put 6? 6 can go here because 5 is already there. You go to the left again. 8 is here. 6 can go to 8. Then where do you go? Do you need to go to the left or you go to the right? Because 6 is smaller than 8, then you have to go to the left. So you place 6 here. I will erase these things. So that is for the left rotation. And another example for the left rotation is this. In this case, we added 2 and it became 4 became unbalanced. And to perform the rotation, we put the temporal node to replace the root node. So we have 5 here, and we take the root node down to the right. And we have 4 here. So this is the final result. And this is the right rotation. Right rotation is similar to the left rotation. The only difference here is that the balance factor of the unbalanced node is +2. And the balance factor of the right child node is -1. So if that is the case, then we need to perform a rotation towards the left in order to make the unbalanced node balance. So let's have a look. So this is a case of a tree that the root node has unbalanced factor of -3 as a result of this node 7 that was added. So we know that what we need to do here is to move it to the left. And how do we do it? If we pull this down, 6 is going to come up, 9 is going to come up a bit, and 7 is going to take this position. Okay, then we are going to have this to be under 6, and 5 is going to be on the left side of 6 as well. So perform that operation. There's no solution here, but I know you can perform it with these examples or this that I've explained to you. Let me do that quickly. So I'm going to have 6, 9 is going to be here, and 7 will still remain its position, retain its position. So when we put it to the right, we expect that 3 is going to come up here, 2 is going to retain its position, and we're left with 5. 5 is at the left-hand side of 6. So we come to this place. We compare 5 with this. 5 is greater than 3, so we're going to move right, and we have to put 5 here. So this is going to be the outcome of this operation, and it is left rotation because we have moved this root node to the left. I'm going to erase this. If you follow this algorithm here, you understand that you finally did a left rotation, and that is why you got the result. So in summary, we have that the left rotation, the balance factor of the unbalanced node is +2, and that of the child is +1. And for the right rotation, the balance factor of the unbalanced node is -2, and that of the child is -1. And these algorithms are the things that are here for you to use to achieve the rotation. So then on this lastly on this, we can say that the child of the unbalanced node replaces the unbalanced node. Let me take this back a bit. So what he's saying is that this is the child of the unbalanced node that replaces the unbalanced node. That's just what the sentence there is saying. Now, we're now going to look at the left rotation with this statement saying that the child replaces the root node. So now the root node is this and the child is this one. So what will you do? It's going to replace this one. And if you replace this one, we have displaced the position of this. So for us to have displayed the position of this, then we have to find where it should stay. And where it's going to stay is going to move to the right. So finally, we're going to have something that looks this way. This is the child going to replace this, and this is going to be displaced to come under here. So this is final result is going to be like this. Okay. Okay, now we are going to learn double rotations. So the double rotations, remember, they can be right left or left right rotations. So for this case, the balance factor is the unbalanced node is right heavy, and the right subroot of that unbalanced node is left heavy. We see an example to that. So again, the balance factor of the unbalanced node is -2, whereas the balance factor of the right child of that unbalanced node is +2. So the kind of operation we are going to perform here is not going to be left-left, or neither is it going to be right-right. So it's going to be right-left operation, okay? So now let's have a look here. So this is an example of where we need to perform the right-left operation. So to perform the right-left operation here, I will demonstrate. So we can move this to the right, okay, by going from here to here. That is K taking the position of P. This is the right move. Then we can move it to the left. How do we move it to the left? Take the position of this. So the final position of K is going to be here. So in that case, we're going to have K at the top root. P is still retaining its position. And what is going to happen to H? So the H has been displaced. The H can go to the left. So at the end, what the result is that we have labeled them roots, and we labeled this T1 and T2. So first of all, we are going to move this. Our plan is to move this to this position. So this is the operation is going to be. K is going to move to this place. And again, K is going to move to this location at the, by doing the next rotation. And at the end, what we're going to have is that we're going to have this structure, which is similar to what we have P here, K here, and H. So another way to explain this is that you can simply say that this value K can directly replace the position of H, and H can move to the left. So if you do that, we're going to have K replacing here and this moving to the left. That's another way to perform the operation. So now moving from the right left rotation, we're going to do left right rotation. Left right rotation is just like the another side of or the opposite of right left rotation. So in this case, the balance factor of the unbalanced node is +2, and the balance factor of the left child of that unbalanced node is +1. And the operation we're going to perform will be left rotation followed by right rotation. So, and there's no example for this, but it's similar to this example that we have here. Okay, all right. So if you have question on this, please let us know. Now let's continue. So in summary, we have the left-right rotation, the right-left rotation, and the balance factor for the left-right rotation the unbalanced node is +2, and the balance factor for the child of the unbalanced node is -1. Similarly, the balance factor of the unbalanced node for the right-left rotation is -2, and that of the child is +1. So these are the kind of operations we're going to perform in each of them. So, and this is an algorithm to represent them. So finally, we can say that the grandchild of the unbalanced node is used to replace the unbalanced node, and that is it for the double rotation. In case of double rotation, the grandchild will be used to replace the unbalanced node. So we're going to see examples in subsequent slides anyway. So let's continue. Now, this is an example where we need to create an AVL tree with using these elements on the nodes. So let's have an example. For us to insert Roy, we insert Roy. Roy is going to take the root node position, and the balance factor is going to be 0 because you have 0 minus 0, which is 0. So we insert another one, we sum to it. So the balance factor of Roy increased to -1, and that of Sam becomes 0. You know why? Because 0 minus 0 is 0. But in this case, 0 minus 1 is going to be -1. Then let's add another Steve. We add Steve here. The balance factor of Roy increased to -2. So what do we need to do? We need to perform a rotation. And what kind of rotation is this? To help us determine, we need to find out what happened to the previous node or the tree we had before that resulted this to Roy becoming unbalanced. And what happened was because we added Steve at the right. So this is going to be a right rotation. And how do we perform the rotation? We can perform the rotation by pulling this thing this way. And when we pull it this way, we're going to have this, or rotate it this way, we're going to have this as our result. So now let's add another node into this. We are adding nodes build. So now we've added build, and we added build to the left. So if we look at the balancing factor of each of these nodes, we can say that the tree is balanced. So we don't need to perform any operation. Let's move to the next one. And we added and to the left. And because we added to the left, it's going to be left heavy, and we're going to perform, this is kind of a left rotation. So where is the first place where we need to perform? We have to perform the balancing, first of all, at the at the child node of Sam. So what kind of operation are we going to perform here? I would like you to think about it before going further. You can pause this video, think about the operation that we need to perform before you play the video again to compare your result with the results we have here. So the kind of operation we're going to perform here is going to be a right rotation, which is based on left rotation. So the right is that we're going to move this way, move it to the right, and moving it to the right, Bill is going to take this position, Roy is going to go to the right, and we have this as the outcome. So let's add another node, the iron. So when we do that, we have that Sam is now heavy in terms of, as a result of a left-right rotation or an addition that was performed to a node that was added to the right. So what do we need to do? We need to balance this node. And the kind of operation we're going to do is that, remember that this is not LL, or um, neither is it RR, that is not left-left and is not right-right rotation. So in this case, you have left-right rotation. And I'll remind you that we said that in terms of left-right rotation or right-left rotation, that the grandchild node can simply replace the unbalanced node. And what is the grandchild node for this case? In this case, the grandchild node is Roy. So we can quickly replace Sam with Roy and move Sam to the right. Or we can perform the left-right rotation. So the left-right rotation is moving Roy to this place. Then the right rotation again is to move Bill to the Roy, which is here down to this location. So when we perform that operation, we're going to have this. And it's the same thing saying move Roy to this location and move Sam to the right. Okay. So let's add another element. We add another element to this. We have added Bob and the tree is balanced. So let's add Jim. We added Jim and the tree is balanced. Let's add another node, dot. We have dot and some trees or some nodes are not balanced. This node is not balanced and that node is not balanced. And the nodes that the first one we're going to perform is the one that is closer to the child node. So then what can we do? We can do the same thing by finding, because this is right-left rotation, by finding which of these nodes here is the grandchild node to Bill. So we know that Bob is the grandchild node to Bill. So what do you think we can do? We can use the operation for replacement, or we perform the operation of rotation using right rotation to the left rotation. So if we do the right rotation, we move Bob to Iron, and we from there move it to Bill. And if we perform the replacement formula, we just replace Bob, which is the grandchild node, with Bill and move Bill to the left. So let's now look at another one. We want to add Mary. So if we add Mary, this becomes unbalanced. And we need to perform operation to make it balanced. So the operation could be performed on this node and looking at the grandchild node. So you can do a direct replacement. And when we do a direct replacement, we can have iron to take this position. So that's what we're going to have. I'm taking this position and we're moving to the right. So we have to add team. When we add team, we have that this node is unbalanced. What do we need to do? We need to perform a rotation to make it balanced. What kind of rotation are we going to perform? That could be right-right rotation because it is -2. So if we perform right-right rotation, remember we have to move this once and this can take the position at the left. So we're done with that one. The outcome is going to be this way. Then let's add another node, which is Tom. When we add Tom, the tree is still balanced, so no operation is required. And there's no other element to add into this tree. This will be the end of our insertion process, or creating a tree with those elements we had. So to summarize what we've done today, we've tried to introduce to you the binary search tree operations, having identified that binary search tree has some limitations in terms of the arrangement. That if we arrange a node with, sorry, a binary search tree with about 3 nodes, we can have different ways to arrange them. And we notice that the shape of that tree will determine the complexity in terms of the height, because the height can be reduced from, for example, the one that is for 3 nodes, we had the maximum height to be 5, to be 3, but we had the minimum height after rotation to be 2. So we can perform rotation on any of these trees to minimize the height. And as we are minimizing the height, we are minimizing the complexity of the program. So yes, and we introduced different ways to do that. One noticeable approach is the AVL tree approach, where we can use single or double operations to achieve the rotation, to make it, to reduce the balance factor of any of these nodes from +or -2 to +or -1 or 0. So at the end of every lecture, we always have an exercise for you to do. And in this workshop 8, we have a couple of exercises on the module that you can try your hands on. So we advise that you try them because it's necessary for you to learn. And if you finally, on attempting them, you could not solve the problem, you are always welcome to bring it to the tutorial sections, or let us know individually on one-on-one appointment, and we can help you get to the solution. This is where we're going to end this section. And thank you so much, and see you next time. Bye.